the topic we're going to introduce now is surface area. This is section 14.5. In your chapter 14 on multiple integration. So we have a formula in this section. First of all, we're told we have a function f of x and y with continuous first partial derivatives, and the function itself is continuous. And we're integrating over a closed region in the xy plane. Then we get to say the area of the surface S given by our function over the region R. So continuous function with continuous first partial derivatives, a closed region R in the xy plane. The formula then is going to be integration over R ds is equal to integration over R, the square root of 1 plus the first partial with respect to x, function of x and y, that squared, plus the first partial with respect to y, function of x and y, that squared, dA. So this is going to be the formula we're working with in this section. And it should look kind of similar to you to the formula that you would have had for surface area in the plane. Now we're doing surface area in space. Okay, so let's look at a first example here. Find the surface area of the portion of the plane z equals 2 minus x minus y that lies above the circle x squared plus y squared less than or equal to 1 in the first quadrant. So the circle x squared plus y squared less than or equal to 1 is the unit circle, and we're in the first quadrant. So this is the region over which we're integrating, but what we're going to be finding is just the surface area of that plane sitting above that region. So our formula tells us, let me write it one more time here, that we need to find the first partial with respect to x and square that. And we need to find the first partial with respect to y and square that. Then add them, add 1, take the square root, and integrate. So first of all, if f of x and y is 2 minus x minus y, then I can say that its first partial with respect to x is minus 1. And its first partial with respect to y is also minus 1. So then we are going to be integrating the square root of 1 plus minus 1 squared plus minus 1 squared, which of course is just square root of 3. So we'll need to set up our integral, and because we have the unit circle as our region, I think it will be pertinent to use polar coordinates. So it looks like my angle theta is running between 0 and pi over 2 because we're in the first quadrant, and the radius of my circle is running between 0 and 1 because it's the unit circle. And I found out that the thing I want to integrate is square root of 3, and because I'm using polar coordinates, I get 1r from my Jacobian, and I'm integrating with respect to r and then with respect to theta. So first integrating with respect to r, I'll pull my constant square root of 3 out. This is r squared over 2. I want to evaluate it between 0 and 1, and then integrate with respect to theta. So that's the square root of 3 times integration 0 to pi over 2. If I evaluate at 1, I get 1/2. If I evaluate at 0, I get 0. So it's just 1/2, which is also a constant. I can say this is square root of 3 over 2. Antiderivative of d theta, or 1 d theta, is theta, and evaluate from 0 to pi over 2. I get square root of 3 over 2 times pi over 2, or square root of 3 pi over 4. So as you can imagine, the most complicated part of these problems is going to come from that square root with the derivative squared. If I have complicated derivatives, my integration might become a little more complicated, but this is just a basic example.